Hello everyone, this lesson is on transformers, electrical transformers, and the first slide here just shows us several different examples of transformers that you might encounter. If you were to take apart one of the electrical appliances in your house, you might find something that looks like this. So that's an example of a transformer. This might just be a few centimeters across, the one that we're taking a look at there. If you have overhead power lines around your house, this power pole that we see here, power lines, and the cylinder, that's a transformer. So this might be, maybe half a meter in length, maybe a meter, and 30, 40 centimeters in diameter. That's a transformer. If you don't have overhead power lines, but you have underground power lines, you might have a green box like this somewhere around your block, and that is a transformer. The one that you might be most familiar with is what you plug in to charge your smartphone, and this is another example of a transformer. So what are transformers really doing? Well, they're taking an incoming voltage and current, and they're changing it. So the outgoing voltage and current is not going to be the same. That more or less is what a transformer does. Changes the voltage, changes the current. I'm going to show you a little YouTube clip here where it's going to show us the different parts of a transformer. And the one that I'm going to show you is called a three-stage transformer. It's a little bit more complicated than other ones that I will show you that are only two stages. So if we take a look at this picture here for starters, what it does show us is kind of arches over here going down the middle. So those parts of it, what we will see is this is going to allow for the transmission of the magnetic field, the magnetic flux, and the three different parts, which makes this a three-stage, three different coils or solenoids, one, two, three. So overall, the way that it's going to work is we're going to have a current that's coming into the first solenoid. We have electrons that are going to be moving through the conductor. And remember, whenever you have a moving charge, that induces or creates a magnetic field. Well, that magnetic field is going to be transmitted through this soft iron core or laminated core. There is no actual connection between the conductors in these different solenoids. What is going to transmit the signal is going to be the induced magnetic field. So electrons going through this solenoid is going to create a magnetic field, which in turn is going to lead to the electrons moving through this solenoid, creating another magnetic field, and in turn inducing the current in the third solenoid as well. So let's just go out of the presentation here and go into YouTube and take a look at this little bit of a clip here. So they start off by showing us the entire transformer, and they're just going to take it apart and then put it back together again. So this is the core that I was talking about. So in this case here, it is a laminated core, a whole bunch of sheets of metal all laminated together. It does not conduct electricity, but it does allow for the magnetic field, the magnetic flux, to be transmitted from one of the solenoids to the other. So this is our central core. It's not showing the entire thing. They still need to cap it off on the top, but they're sliding these solenoids over top. So these solenoids, again, they're going to have many, many wraps of wire relative to their length. And by varying the number of turns in these solenoids, that's what's going to allow us to change the voltage and change the current. So again, each one of these is independent from the others in terms of the electricity that's flowing through them. So in our solenoid on the left-hand side here, there would be a wire connected to it, and that a wire would allow the electrons to flow through it. There's no connection though between this solenoid, the one in the middle, and the one on the right-hand side. So how can we get the electrons going in this middle solenoid here? By generating a magnetic field. So as soon as the electrons are going through our first solenoid, it generates a magnetic field. That's transmitted through the core, which in turn induces the electron movement in the second solenoid. That magnetic field is then going to induce the current in the third solenoid. So again, by varying the number of turns in these coils in the different solenoids. That's what's going to allow for the changing of the voltage and the changing of the current from the voltage coming in compared to the voltage going out, the current coming in compared to the current going out. So they're showing us here just the cap that they put on top here, the remainder of the transformer that we do have, and then they're just going to put it into the transformer box. And the transformer box, usually some sort of cooling mechanism as well, whether it is air cooled or fluid cooled, and then the cap on. So that overall is the basic sort of layout and the parts that we have for a transformer. So this simple picture here is showing us not a 3-stage, but just a 2-stage transformer. So the gray area that we do see here, this is the region of the transformer, the part of the transformer, which is the core. It is not actually transmitting the electrical current. It is not a conductive material. What is a conductive material is what we see in red here, these red lines, and the blue lines on either side of this non-conductive core. But what this core does allow for is the magnetic field to be shared between the two different sides or the two different solenoids. We've talked previously about any time that we do have a current, electrons that are moving as they will be through these red wires, that's going to set up a magnetic field. So that magnetic field is then going to lead to the movement of electrons in the other solenoid. So these two solenoids, again, they are not connected together. They are completely separate. What is allowing for the connection and the movement of electrons on the right-hand side is simply the induction of the magnetic field. As I have at the top here, induction of current on the secondary coil only works by having a fluctuating magnetic field. And the only way that you can get a fluctuating magnetic field, and we're going to see this on another simulation here, is by having alternating current as opposed to direct current. Direct current is simply not going to work with these solenoids and with these transformers. So what else do we have as part of this transformer besides just our metal core that we have in the middle here, the non-conducting core? On the left-hand side, they've identified this as the primary side. N is the number of turns, P is for primary. So we have a certain number of turns on the primary side, the number of times that this conductor is wrapped around the core on the left-hand side. We then have a current. Remember, I is the symbol for current on the primary side that's coming in, and what's pushing those electrons, the voltage. Vp is the voltage on the primary side. So as those electrons are moving, again, they're going to set up a magnetic field, and that magnetic field is then going to also induce the movement of the electrons on the right-hand side. So the right-hand side, this is our secondary coil or our secondary solenoid. So again, we have a number of turns, only this time it's S, the S for the secondary. It's going to change the current on the secondary compared to the primary side. So this is our IF, and that will also produce a voltage that is different on the secondary side, or the VS. So the reason why it does change the voltage really has to do with the number of turns. So in this case here, what we see is that there are more turns on the left-hand side, and there are fewer turns on the right-hand side. So because we're going from more to fewer turns, what that is going to do to the voltage is it's going to decrease the voltage. And for that reason, that is what we call a step-down transformer. If we flip it around and we had fewer turns on the primary side, more turns on the secondary side, that would do the opposite. That would bring the voltage up, and that's what we would then refer to as a step-up transformer. And we'll get into some calculations on those in the next couple of slides here. But first of all, let's just take a look at another clip here, another nice little animation that is showing us a transformer in the middle here. So again, everything that we see in white, that is going to be the core of the transformer that is non-conductive. but does allow for the magnetic field generated on the primary side to influence the current on the secondary side. So we're taking a look at the primary side on the left, and this is our power line that's bringing the energy into someone's house or into the school. So if I just change this over this switch here to DC current, let's do that first of all. So we can see that there is a current, or there is a voltage rather, on the primary side, but there is 0 on the secondary side. So what that tells us is that transformers don't work for direct current. They only work for alternating current. So for alternating current, just as a reminder, what that means is that the electrons go in one direction in the conductor, they stop for a fraction of a second, and then they go in the opposite direction. They stop again, and they just jiggle back and forth, and that is what alternating current is. That's also what it shows us in the graph at the upper left-hand side here. So where we see this sinusoidal curve, that is an indication of alternating current. The nice thing about this animation is it allows us to change the voltage on the primary side. We can change the number of turns on the primary side. We can change the number of turns on the secondary side. And then the graph on the secondary side, that's going to tell us what voltage we actually transformed it into. So what I have it set here initially is the typical voltage on the power lines in your back alley or underneath the ground that come into a transformer, and it might be around 5,000 volts. So quite a high voltage, much, much higher than what electrical appliances run off of in your house. So what you would need to do is bring that voltage down. You would need a step down transformer to decrease the voltage considerably. So the two wires that come into your house, they typically each carry 110 volts. You have two of those coming into your house, so 220 volts in total. So what's going on with the transformer here? We want it to step down the voltage, so we would have many, many more wires on the primary side and many fewer on the secondary side. So here I have it at 1,000 turns on the primary side and only 50 turns on the secondary side. So voltage on the primary side, this is times 10 to the 2. So 50 times 10 to the 2 is 5,000 volts on the primary side. If we take a look at on the secondary side, this is 2 times 10 to the 2. So it is between 2 and 300 volts that we have transformed it to on the secondary side. So again, this would be a step down transformer. We're decreasing the voltage on the secondary side compared to on the primary side. How did we do that? We used a transformer, and we had many, many more turns on the primary compared to on the secondary side. But that is a step down transformer. What if we wanted to do the reverse? What if we wanted to instead bump up the voltage on the secondary side? So now let's just decrease the voltage here to about 240. And I'm going to change the number of turns on the primary side to 100. And I'm going to increase the number on the secondary side, and let's bump it right up to 1,000. So what we have here is a 1 to 10 ratio. We have 10 times more turns on the secondary side than what we have on the primary side. If we have the same thickness of wire, the same gauge of wire, what that should do is it should make the voltage 10 times greater on the secondary side. So if we have 240 volts coming in, 10 times greater on the secondary side. And if we do take a look at that, that is in fact exactly what we have here. So this is about 2.4, but it's 2.4 times 10 to the 3. So that is 10 times higher than what we do have on the primary side. So nice ratio that we do have here. This one then would be a step up transformer. We have many, many more turns on the secondary side compared to the primary side. That's going to bump up the voltage on the secondary side because we have 10 times more turns, the voltage ends up being 10 times greater on the secondary side than on the primary side. And that's a nice ratio for you to keep in mind for your calculations as well. In your data booklet, these are the formulas for electricity. So we already know, of course, the one for current, capital I for current measured in units of amps, capital V for voltage measured in units of volts, and just one equation that we have for transformers, ideal transformers down here. And again, it tells us everything. It tells us that N is the number of turns. Lowercase p is for the primary side. Lowercase s is for the secondary side. So I'm going to do a couple of calculations with you here, where we're going to be using this variation of it. But just realize you can also do calculations where you're asked to solve for the current on the secondary or the primary side as well. So this first one here is going to be for a step-up transformer. So electrical energy, it is transmitted through power lines more efficiently or with less loss of energy in the form of heat when it's transmitted in very, very high voltages. So overhead power lines that are coming from an electrical generating station, they might be transmitting that energy at 200 kilovolts. So 200,000 volts, very, very high voltage and very unsafe voltage in terms of that energy coming into your house. A step-up transformer, though, is going to bump it up to this very, very high voltage. So coming out of an electrical generating station, it's actually not that high. It might only be somewhere on the order of, we'll say, 20,000 volts, maybe even less than that. And if we want to bump it up to the 200,000, that would then be a step-up transformer. So because it is a step up, the transformer would have many, many more turns on the secondary side compared to the primary side. So this is what would increase the voltage prior to transmission through these high voltage power lines. So yes, it increases the voltage on the secondary side by having more turns on the secondary side. So this example here, calculate the number of turns is what we are in fact calculating on the secondary side to increase the voltage from 220 to 11,000 volts. And the number of turns on the primary side we're seeing is just 20 volts. So remember that I always like you to show all of your information, which does mean grasp. So first of all, what is the given information? Well, we're given some numbers here, of course. We are given a voltage on the primary side that we're starting with, and it is 220 volts. We are given a voltage on the secondary side, what we were stepping it up to, and that is 11,000 volts, so considerably higher. We're given the number of turns on the primary side, which is 20. All of that is our given information. What are we asked for? Our required information? Well, that is going to be the number of turns on the secondary side. That's what we're trying to find out. So again, in your data booklet, you do have the equation for this. So if I just write down that whole equation again, so NP, number of turns on the primary, divided by the number of turns on the secondary side, is equal to the voltage on the primary side divided by the voltage on the secondary side. So in this case here, what we're actually asked to calculate for is this one. So you need to isolate this, get it on its own. Everything else needs to go over to the other side. So we're going to have our NP, VP, VS on one side, NS on its own on the other side. So let me show you one way to rearrange this equation right now. So if I want to get NS on its own, first of all, I need it in the numerator and it's in the denominator. But all I need to do is move it to the other side, and then it's in the numerator. It's in the denominator on one side. If I move it to the other side of the equal sign, I need to put it in the numerator. VP, I need to move it to the other side, the left-hand side in this case. It's in the numerator. If I move it to the other side, it ends up in the denominator. So I'm actually just going to flip those two around. VS, I need to get it to the other side. It's in the denominator. So I'm going to put it up in the numerator. Tidying all of that up, what does that give us? Number of turns on the secondary side, which is what we're trying to find out here, is equal to the number of turns on the primary times the voltage on the secondary side divided by the voltage on the primary side. So we already have all of this information, of course, we just need to plug it in. So the number of turns on the primary side, that is the 20 turns. Voltage on the secondary side, what we're stepping it up to is 11,000 volts. And the voltage that we have on the primary side, that was our 220 volts. Volts cancel out. What we're left with is turns, and that is what we do want. So because this is a step-up transformer, what we should find is that the number of turns is considerably more on the secondary side compared to the primary side. And when you plug these numbers in, well, it is 1,000 turns that we now have on the secondary side. So in terms of the grasp, again, we had the given, required information. Analysis is the equation, and then solving it is plugging in the numbers and coming up with the answer that we have right here. A step-up transformer bumps up the voltage, more turns on the secondary side than what you find on the primary side. Just one more here, we'll just do exactly the opposite. So this one is a step-down transformer. So devices in your house, most of them plug-in devices, they operate off of 110 or 220 volts. So if you have a dryer, it will run off of 220 volts. Electric range oven will run off of 220 volts, but most of the appliances in your house, they do operate off of 110 volts. So the power line in your back alley or underneath the ground, coming into the transformer, it might have a voltage of 4,000 volts or 4 kilovolts. So it needs to be bumped down to a lower voltage, and that would then be a step-down transformer, which means there would be fewer turns on the secondary side than on the primary side. So yes, what we're doing is we're decreasing the voltage coming out of the transformer. So here we have calculate the voltage on the primary side. Voltage on the primary side is what we're being asked for. That is our required information. We're given here the number of turns, 300 turns on the primary side. NP is equal to 300 turns. We're given the number of turns on the secondary side, and S is equal to 40 turns. And finally, we're also given the voltage on the secondary side, and this would be 9 volts that we have. So we are given the number of turns, and we can see that there are many, many more on the primary than on the secondary side. So that is a step-down transformer. We end up with the voltage of 9 volts, which means this one here, the incoming voltage is going to be considerably higher. So kind of think your way through it. So when you do come up with an answer at the end, ask yourself the question, is it a reasonable answer that you have come up with? So again, our equation, I'll write it down one more time. NP divided by NS is equal to VP divided by VS. That previous one was actually more difficult to manipulate than this one. Here we're solving for the VP. Let me show you another way to get rid of this VS. So if it's in the numerator and I want to get rid of it, I need to multiply by the same thing in the numerator. Okay, they then cancel out. The rule is whatever you do on one side, you need to do to the other side of the equal sign. So if I multiply it by VS on the right-hand side, I need to multiply by VS on the left-hand side. So tidying that all up, what am I solving for? Voltage on the primary side. It's equal to the voltage on the secondary side times the number of turns on the primary side divided by the number of turns on the secondary side. Let's go ahead and plug those numbers in. So we have 300 turns on the primary side, multiplying by the number of turns on, or sorry, the voltage on the secondary side. So that is our 9 volts that we do have, and we're going to divide that by the number of turns on the secondary side, which is our 40 turns. Turns cancel out. We're left with volts, which is what we want. Plug these numbers into your calculator. So this is the voltage on the primary side. Remember, we predicted that it would be higher. Plug the numbers in, and you get a number of 67.5 volts, which is higher. So it seems like a reasonable answer for this step-down transformer.